Hello, and welcome back to my YouTube channel. Today I'm going to be talking to you about the common emitter, NPN, BJT with emitter degeneration. And essentially we're going to label some things here, starting with our transistor. We're going to label this node here as C, this here as B for base, and this here as E for emitter. And it's called a common emitter because the emitter is connected to ground, so it's common, and we have a degeneration resistance right here, so that's where it gets its name from. Next, we're going to label some different currents. So when we talk about IN basically flows like this, comes in here, and it gets split within these three paths. Okay. And these two get put out here. So I'm going to call this path IE. And then when it comes to backwards, we could talk about a current IO flowing over here and then getting split over here. And an important current is IO1 that we're going to be using. But for now, let's dive into what we're going to be solving. And specifically what we need to solve is for RN, Rout, and AV. So let's start with Rout. And we say that, let's start with RN. And we say that Rn is equals to Vn over In. And the first thing we can do is we can write a KVL right here, where we can consider that the voltage drop across Re is Ve. So we could say that this is minus Vn plus V pi, which is just VBE, plus VE is equals to 0. Again, where V pi is equals to VBE. So then we can go ahead and say that this is Vn is equals to the current and resistance of V pi, which is In times R pi plus Re IE, which is equals to 0. Which is, that's the equation. Let's say that this is equation 1. Using some BJT rules of currents, we can say that IE is equals to 1 plus beta IB, where again IB is just In because this is In right here, which is connected to the base. So then this is equals to 1 plus beta In. So then this is our second equation. So let's go ahead and plug IE into this equation. So let's go ahead and plug this into here. We then get that Vn is equals to In R pi plus Re 1 plus beta In. If we keep on going, this is Vn. We could pull out an In, and we're left with R pi plus Re 1 plus beta. And then since we said Rn is equals to Vn over In, this is then equals to R pi plus Re 1 plus beta. And if you see here, R pi is regularly a lot bigger than RE because it's related to the transistor. So then we can say that Rn is basically R pi. So this is the full solution, and this is the approximate solution, which will still get you close to the right answers if you do simulations. So now let's go ahead and talk about R out, the proof for R out in this situation. Use purple. And R out is a bit tricky because what we're going to do is we're going to say that R out we're going to say that R out is equals to V out over I out when V in is equals to 0. So I'm going to redraw the small signal down here. And essentially what it looks like is we have this R V in grounded. We have a resistor R pi, another resistor RE. So this is R pi RE that flows into a voltage controlled current source GM-VBE. Again, this is VBE or V pi. This is RO. And we have this RC, which has a drop V out across it. So now if we go ahead and label our input current, so this is IO, this is IO1, and then the IO1 comes, the IO, the input output current comes out to here, but then it gets split again here, right? But here is a resistance, or two resistance in parallel. So if I can draw this in a different color, imagine this is R pi. Get rid of this. And it has a drop VBE through it. So then I could consider then now that this entire thing, right, is just one resistance in parallel. So again, we can consider that this total thing is this RE in parallel with R pi, where the drop across from it is VBE since they're in parallel. So now we can say that this entire thing to ground is IO. So I hope this manipulation of our small signal makes sense, because we're going to need it now to write out some KVLs and KCLs. We're going to start off by writing a KCL. So we're going to solve for current. And we're going to say that IO is equals to IO1 plus GMVBE. Again, that's just the split between this RO and here. The next equation we're going to write is an equation for VBE. So we're going to say that VBE is equals to an RE in parallel with R pi times IO. So this is my first equation. This is my second equation. And for my last equation, I'm going to write a KVL in this loop. Okay. So loop 1, or I'll just label that just this loop, and then I'm going to write, so it's minus V out plus RO IO minus GM VBE. Okay. And actually, let me be explicit. So let me do ROIO1 plus an RE in parallel with R pi IO. This is equals to 0. So now what we're going to do is we're going to manipulate this IO. We're going to say this is IO1 is equals to IO minus GM VBE. And we're going to take this and plug it in here. And then we're going to go ahead and also plug in VBE in here. But I will do this in 2 steps. So the first step is minus VO plus RO, IO minus GM VBE plus RE in parallel with R pi IO is equals to 0. Go ahead and plug in VBE here. So then we get minus VO plus RO, IO minus GM RE in parallel with R pi times IO plus RE in parallel with R pi times IO is equals to 0. I'm going to go ahead and move the V out to the right hand side. So then I get RO IO minus RO GM RE in parallel with R pi times IO plus RE in parallel with R pi times IO is equals to VO. We can then say that R out is equals to V out over IO, which is then equals to RO plus GM RE parallel with R pi RO plus RE parallel with R pi. And some simplifications we can do is we can say we can pull out an RE, R pi, and we could say then that R out is equals to 1 plus GM RO times RE parallel with R pi plus RO. So this is your general solution. This is your final solution. But normally we say then that if RO is much greater than RE parallel with R pi, which is normally the case, then this middle term is the only thing that will stick. So R out is equals to GM RO RE parallel with R pi. So this is your approximated with high accuracy solution. So the next thing we're going to talk about is the AV gain, or the voltage gain. And again, we're going to write some KVLs and KCLs and see if we can get AV, which is equals to the VO, or the V output, over V in. I'm going to make a general approximation here, and I'm going to say that in a BJT, if I have a current IE, this will equal current IC. In this circuit, if I were to label some things here, this is IO, which is equals to IC. This should be C, and this should be E. And this here is IE, which is equals to IO as well. So essentially we're going to say IC is equals to IE, or IO is equals to IE. So I hope that makes sense with this approximation. And normally in a BJT, the I beta is extremely small. The current coming from the base is extremely small, where this approximation is valid. So the first thing we're going to do is we're going to write a KVL in this loop. So KVL through loop 1. And I'm going to say then that minus Vin plus VBE plus RE, we know IE is just IO, is equals to 0. And then let's solve for VBE, which is equals to Vn minus RE IO. Let's consider this equation 1. If I wanted to then write an equation for IO, IO equation, where I want to write the equation for IO going through this loop, I can say then that this is 0 volts. This here is VO. So I could say IO is equals to 0 minus VO over RC, which is just equals to VO over RC. The next thing I can do is I can write a KCL equation for IO. And I could say then that IO is equals to IO1 plus GM VBE. And again, I get this from IO flowing through here. There's a IO1 here, and there's a voltage controlled current source, GM VBE. So then let's go ahead and solve for IO1. So we could say IO1 is equals to IO plus GM VBE. Let's also go ahead and substitute IO equation in here. And let's go ahead and substitute VBE, the equation, in here. So then I get that this is IO1 is equals to minus VO over RC plus GM VBE. Sorry, this should be Vn minus Rn IO, which then equates to minus VO over RC plus GM Vn minus GM RE. Again, IO plugs it into here, and we get minus VO over RC. So I hope that makes sense. So the last thing we're going to write, I'm going to switch colors, is a KVL in this loop. Okay, so we're going to get minus VO plus RO times IO1 plus RE times IO. So let's go ahead and write that down. So then this is going to be KVL at 2. Again, where this is 2, loop 2. And we're going to say then that this is minus VO plus RO IO1 plus RE IO, which is equals to 0. We can go ahead and plug in for IO1. This is VO plus RO. I'm going to distribute my RO to all these terms. So RO minus VO over RC minus, so I made a mistake here. In this IO1, there should be a minus sign here because I'm subtracting GM VBE. As a result of that, there should be a minus sign here, and then this switches to a minus and a plus. Okay, I hope that makes sense. So let's continue. So then this should be minus GM Vn RO plus GM RE times minus VO over RC RO, and then plus RE times an IO, which is just, again, this minus VO over RC is equals to 0. So then let's go ahead and move all the terms that have VOs in them to the right-hand side. So then we get that this is VO. Let me use a different color. We get that this is VO 1 plus RO over RC plus RO GM RE over RC, and then the last term we get is plus RE over RC is equals to VN, and then it's a minus GM RO. We then say then that AV, which is equals to VO over VN, is equals to minus GM RO over 1 plus RO over RC plus ROGM RE over RC plus RE over RC. If I go ahead and multiply this by RC on top and bottom, I get then that this is equals to minus GM RO times RC over 1 plus RO plus ROGM RE plus RE is equals to AV. Generally speaking, we consider RO to be much greater than RE and much greater than RC. As a result of that, in the eyes of, so AV is equals to minus GM. In the eyes of RC and RE, they see RO as basically infinity. This could be, since RO is infinity, this whole bottom denominator becomes infinity, and this cancels out. So then we're left with minus GM RC is equals to AV. And this is the total solution, and this is the approximation solution with very high accuracies. Again, the only thing we approximated or we considered was that IC is equals to IE, which again, when dealing with BGTs in the saturation region, that is the case. So I hope this makes sense. In this video, we solved for AV gain, R out, and R in. And as you can see, the further right we went, the more complex it became. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Again, like, share, and subscribe to my YouTube channel. Thank you.